Hi everyone, Professor Bob Young back here, and in this instructional video we're going to look at the exponential growth or decay function, some growth function models, and some decay function models. Now I'll probably have to break this up into a couple of videos here because there's a lot of things to look at. So first we're going to start with exponential growth or decay function. And it says in many situations that occur in ecology, biology, economics, and the social sciences, a quantity changes at a rate proportional to the amount present. In such cases, the amount present at time t is a special function of t called an exponential growth or decay function. So here it is, let y sub naught be the amount or number present at time t equals 0, then under certain conditions, the amount present at any time t can be modeled by this function, y equals y sub naught e raised to the kt power, where k is some constant number, and of course t will be represented by some time. So when k is greater than 0, that constant number, the function describes growth. And in a previous lesson, we saw examples of exponential growth, compound interest, and atmospheric carbon dioxide and stuff we looked at for the CO2 levels and global warming and stuff. And when k is less than 0, the function describes decay. One example of exponential decay is radioactivity. All right, now, if you remember a while back, and this was several videos ago, we discussed the growth of atmospheric carbon dioxide over time. A function based on the data from the table was given in that example. Now we can see how to determine such a function from the data. So here is the chart one more time from the year 1990 to 2275 projected, and the amount of carbon dioxide in parts per million. And boy, we better really start looking at this and get these numbers under control, or who knows what. But anyway, hopefully math will help us in the long run. It says find an exponential function that gives the amount of carbon dioxide y in year t. Now, recall that the graph of the data point showed exponential growth. So the equation will take this form, y equals y sub naught e to the kt power, and we must find values of y sub naught and k. Now the data began with the year 1990, so to simplify our work, we're going to let 1990 correspond to what? T equals 0. So let's go ahead and start locking in on some things here. So 1990 t is going to be 0. 1991 t is 1, and so on. So y sub naught is the initial amount is going to be 353 in 1990. That's when t was equal to 0. So right here, we're just going to go ahead and call this t equals 0 and so forth. Okay, so it's nice being able to back up. All right, thus the equation here, if we start out t equals 0, y equals 353 e to the kt power. So notice when that is 0, when that time is 0, we get this. And e to the 0 power, so when at time t equals 0, k times 0 is 0, and we would definitely get 353, wouldn't we, in our chart? So that's a good starting place. All right, so from the last pair of values in the table, we know that in 2275, the carbon dioxide level is expected to be 2,000 parts per million. The year 2275 corresponds to 2275 minus 1990 is 285. So it says substitute 2,000 for y and 285 for t to solve for k. So what we're going to do here is we're going to, in the next graphic, put 2,000 in here and 285 in here. All right, from the data points, because we've already got year 1 here, we know is 353, and we can solve and get that constant of proportionality. So once again, we are solving an exponential equation. All right, so divide both sides by 353, so y'all can kind of see that one here. And I'll go through, you know me, Young goes through and shows steps, step by step by step. We multiplied this constant by that 285 number here, all right, and got 285K. And now to undo the E, we're going to ln both sides of the equation. And again, here's that rule again. It just keeps coming back and coming back. So 285K, the ln undoes the E, gives us that power, equals the ln of 2000 over 353. And solving for K, we get about 0.00609, and use your calculator here. Make sure you get that same number. So a function that models that data from those CO2 emissions is now looking good. Here it is. So that is an exponential growth model since this K number here is greater than 0. Unfortunately, the carbon dioxide seems to be increasing in the atmosphere as measured by the chart. All right, now we can do other things here with this. Now that we've got this model, it says estimate the year in which future levels of carbon dioxide will double the 1951 level of 280 parts per million. All right, so what we're doing is we're going to put in 560, which is twice 280, into this formula here and solve. So you can really use this in real life. And then again, we're going to go ahead and solve this, divide both sides by 353. Take the ln of both sides here, which is going to knock that power right off of the E there. And then the time will be solving 75.8 years. So since T equals 0 corresponded to our 1990 level there, the 1951 carbon dioxide level will double in the 75th year after 1990 or during the year 2065. So lots of things you can do as far as using these type things in real life. All right, now it's time to go back to your banker and money. And there's our friend, the PERT formula, the shampoo formula for continuous compounding we haven't seen in a while. Woohoo! Says, how long will it take for the money in an account that is compounded continuously at 3% interest to double? Time to double. All right, so if we're investing amount of money P here, and it could be $1, then think about this. The time to double would be, well, 2P, $2. Or this could be, P could be $10, $20, $1,000, $2,000, $1 million, $2 million, and so forth. So then we can easily find the time to double or triple using the PERT formula, divide both sides by P. And notice the time to double here would just give us a 2 equals E, and of course we've got 3% as 0.03 T. Again, ln both sides, you know where that power is going to go right here, don't you? It's going to go poof right out. This sure looks a lot nicer than some of those other formulas. And we get the ln of 2 equals 0.03 T. Dividing by 0.03, it's going to take about 23 years for that amount to double at 3% interest. It's almost, I don't even think my bank gives me 3%. And if you took my account and doubled it, well, let's not go there, Young. It's a sad day. All right, one last example, and we'll go on the next video and do some others. We like to give you lots of examples here. All right. According to the U.S. Census Bureau, the world population reached 6 billion on July 18, 1999, and was growing exponentially. And these are usually true things in these word problems, so this is kind of interesting stuff too. By the end of 2000, the population had grown to 6.079 billion. The projected world population in billions of people T years after 2000 is given by this function. So 6.079 e to the 0.0126 t power. Based on the model, what will the world population be in 2010? Okay, so if we go ahead and put 10 in for t, we're going to get about 6.895 billion. All right, so make sure that you can, on your calculator, put in these values here. So let's just refresh your memory on how to enter it. It would be 6.079 e raised to the parentheses 0.0126 times 10 power close. And this is a caret in here. That's a bad caret. Let me fix that caret. And you should get about 6.895. So again, make sure you and your calculators are 1 in this section. One more example, and we'll sign off on this video. In what year will the population reach 7 billion? So we can put 7 in for the y value, f of t, and solve here. So what they did here is they divided both sides by our initial value there, 6.079. As you can see, ln both sides, which you know is going to pop that power right off of there. And solving, it's going to take 11.2 years after 2000. So the world population will reach 7 billion during the year 2011, which is the year I'm actually doing this video. It's actually March 18th, 2011 as I do this. So with that in mind, Bob Young signing off. I'll see you in the next video. Hit that homework.